As we've seen before on space-time, gravity affects the motion of all objects identically. So if gravity from the moon and the sun is really responsible for tides in the ocean, and water is water, then why don't we see tides in lakes? Guess what? Whatever you believe about why ocean tides exist is probably wrong, even at the most basic level. In fact, every YouTube video I've ever seen about tides, including ones made by smart people, explains the tides incorrectly. Typically, they show this diagram along with an explanation that goes something like this. The moon's gravity is stronger at point A and weaker at point B than it is at Earth's center. The net effect of this differential in the moon's gravity across the Earth is to stretch the oceans out like taffy, ergo why the oceans bulge out at opposite points along the Earth-Moon line. Now that explanation sounds plausible, and a lot of well-known scientists give it, but as we'll see, it's not correct. Don't get me wrong, the facts are correct. There really is a gravity differential from the moon at points A and B, and at least in this simplified model, there would be two tidal bulges at opposite ends of the Earth-Moon line. Plus, if Earth could rotate underneath those bulges with no friction between the ocean and Earth's crust, then at a given location on the globe, you would experience 2 high tides per day as you pass through each bulge, and 2 low tides per day as you pass through the spots at 90 degrees to the bulge. All of that is true. What's wrong is the explanation for the bulges. They aren't actually being lifted or stretched by that gravitational differential. Something much more subtle is happening that even many professional astronomers and physicists misunderstand, including me for many years. So don't feel bad, tides are tricky. But today, we're gonna set the record straight, and in the process, understand how it could be that the ocean has tides, but lakes, bathtubs, and cups of coffee don't. So right up front, I wanna make some assumptions to simplify the analysis and to remove unimportant factors from the picture. That way, we can better isolate qualitatively what's really causing the tides. Here we go. Assumption 1, we're gonna use Newtonian gravity. It's not that Einstein can't explain tides, he can, but curved spacetime will only add complexity without actually making things clearer. Assumption 2, let's ignore the sun. For simplicity, we'll focus only on the influence of the moon. The sun's effects are gonna work analogously anyway. Assumption 3, we're gonna pretend the Earth is uniformly covered with one humongous ocean and no continents. And finally, assumption 4, we're gonna pretend that we can switch Earth's gravity on and off whenever we want to. You got it? Okay. Let's take a closer look at the moon's gravity differential and how it manifests itself from the perspective of a frame of reference attached to Earth's center. Forget about the oceans for a minute and just imagine 2 small blocks, A and B, at opposite ends of the Earth's surface along the Earth-Moon line. Turn off Earth's gravity. What happens to the blocks? Well, relative to a frame out in the ambient space, block A accelerates toward the moon more than Earth's center, and Earth's center accelerates toward the moon more than block B. So from the perspective of Earth's frame, both blocks will separate from the surface, as if acted on by some invisible outward force. That weird invisible outward force is called the tidal force, and in Newtonian physics, it's fake. It's an artifact of Earth's frame of reference. Remember, Earth itself is accelerating toward the moon, so according to Newton, Earth's frame is non-inertial. Now, if you need a refresher on non-inertial frames, you can check out our earlier video on the topic. But the bottom line is that in Earth's frame, the tidal force looks like anti-gravity, at least along the Earth-Moon line. And here's the thing. Just like the fake forces that you perceive in an accelerating train car, tidal forces should make all objects accelerate off the surface identically, regardless of their mass. An object's resulting acceleration relative to Earth's surface is called the tidal acceleration of that object, and it should be identical for a pebble and a pony. But if that's true, the tidal force along the Earth-Moon line can't be raising or stretching the 2 bulges that lie along that line. Because if that were the case, then water in lakes should also be lifted. And for that matter, so should sand and rocks and you. Remember, the object's mass doesn't matter. But we don't see things levitate during high tide. More important, the math of assuming the bulges are being lifted doesn't work out. The tidal acceleration on objects due to the moon's differential gravity along the Earth-Moon line works out to only 1/10 millionth of an Earth G. And you can't lift something by pulling up on it with a force that's 10 million times smaller than its Earth weight. Plus, even if you turned Earth's gravity off, you would never notice an outward acceleration of 1 micron per second. Nevertheless, those bulges in the ocean are real. So if the ocean isn't being stretched, then how do they get there? The key is to look at the tidal acceleration of objects that are not on the Earth-Moon line. For instance, a block at this location is going to be pulled this way by the moon. But of course, the whole Earth is pulled that way by the moon, chasing after the block. So relative to the Earth's surface, the block's tidal acceleration is almost radially inward, in other words, down. In fact, if we map out the tidal acceleration vectors that you'd see at different points on Earth's surface, they look like this. As you can see, tidal forces only act like anti-gravity if you're right on the Earth-Moon line. At most places, those vectors are largely tangent to Earth's surface, which would push water sideways. Now, we've drawn these vectors kind of big to help you visualize them, but in reality, they're microscopic. Remember, the radially inward acceleration caused by Earth's own gravity on objects is 10 million times bigger. However, the surface area of the ocean is also enormous, so those tiny tangential sideways pushes on all the chunks of water added up over half the surface of the planet can produce a pretty decent increase in water pressure. So I think you can start to see what's happening here. The ocean isn't being lifted or stretched. Instead, thanks to the cumulative sideways traction everywhere else, it's being squeezed toward the Earth-Moon line and piling up there. Basically, the moon is turning the entire ocean into a planet-sized hydraulic pump, and the ocean is bulging along the Earth-Moon line in the same way that a blister or a pimple will bulge up in the center if you start to squeeze it from the side. So why don't lakes have tides? Well, largely for the same reason that it's very hard to pop small pimples: less traction and bad hydraulics. See, unlike the oceans, a single lake is not a contiguous planet-sized body of water. Lakes just don't have enough area for the tiny pushes on it to build up enough pressure to change the water level. Now, technically, really big lakes like Lake Michigan in North America can generate enough pressure to produce mini tides, maybe with a couple of centimeters difference between low and high tide. But since winds and boats and aquatic sloshing will all create ripples that are way bigger than that, those mini tides just aren't noticeable. The same is true for any enclosed body of liquid. A swimming pool, a bathtub, a human body, which is basically a big sack of water, and a cup of coffee technically all experience tides. They're just microscopic. Also, remember that Earth itself isn't perfectly rigid, so when water in a swimming pool rises a tiny amount, Earth's surface is also rising by a tiny amount, making the change in water level relative to the surface of the planet even less noticeable. Now, everything that I've just said is oversimplified, but I think it gets the main point across. Namely, tides have a lot more in common with pimples than they do with taffy. Okay, we've got a few loose ends to tie up. First, the sun. Its effects on tides are analogous to those of the moon, but they're only about a third as big. The sun is more massive, yes, but it's also much further away. Now, when Earth, the moon, and the sun all line up in space, the effects are additive and you get extra large spring tides. When instead they make a 90-degree angle in space, there's partial cancellation and you get extra small neap tides. Second, in the simple model of a water world Earth, the math says that the water level should vary by about 3/4 of a meter between high and low tide. But some places see smaller tides than this, while other places like the Bay of Fundy in Canada have tidal swings of over 10 meters each day. So why the variations from place to place? Well, location relative to the plane of the moon's orbit is certainly part of it, but mostly it's that nooks and crannies in the continents affect the details of how pressure gets distributed through the ocean in non-uniform ways. For example, some lakes and rivers that have direct ocean inlets do have tides, but instead of rising gradually, high tide can come in through the inlet like a moving wall of water called a tidal bore, which is pretty cool. Also, some variation in water level is just sloshing that's not directly related to tides at all. The bottom line is that the finer details of tides in the real world are just kind of complicated. So are other things that I haven't mentioned, like how the rate of Earth's rotation and the ocean tides affect each other. For discussions of all of that, I humbly direct you to other videos and articles that are linked down in the description. Finally, Porsche911, one of our viewers, once asked how Miller's planet in the movie Interstellar could have had such huge waves without the astronauts themselves being stretched or levitated. I think that other stuff was supposed to be at play there, but nevertheless, when it comes to liquid on a planet, the squeezing aspect of tidal forces will almost always be more important than the stretching, even in the craziest regions of spacetime. Last week, we finished our series on general relativity and curved spacetime. You guys had a lot of great questions that I'll address in a second, but first, a comment about one of our earlier episodes. A while back, we did an episode clarifying misconceptions about so-called habitable exoplanets. Now, prior to the airing of that episode, at the 2015 NASA Space Apps Challenge, a colleague of mine, Professor Emily Rice from the College of Staten Island, had done a very similar talk about exoplanet atmospheres. She and I had been talking about exoplanets back and forth for a while, including in the context of this show, and there was a lot of overlap between our two talks that I wasn't aware of at the time that we aired our episode. If I had been, I would have cited her talk explicitly explicitly, and I'd like to rectify the situation now. So down in the description, you'll see a link to her talk about alien atmospheres. It's very good at the NASA Space Apps Challenge, along with a link to other information from her website. Now to your comments. A lot of you ended up asking very similar questions. Rather than address your comments individually, I'm going to address the most frequently asked questions in bulk. A lot of you asked about gravitons in the following context. You may have heard that in quantum field theory, forces are described as being mediated by some kind of particle, like electromagnetism by the photon, strong nuclear forces by the gluon, and so forth. So if gravity is not a force and it's considered space-time curvature, then why do people talk about gravitons? That's an excellent question, and it's hard to answer. But here's the rough bottom line. Thinking about things in terms of gravitons and thinking about space-time curvature are not necessarily mutually exclusive. It's just that instead of quantizing a sort of standard field that you think of as a force field, you're quantizing something different when you talk about the quantum version of general relativity. And it turns out that you can do it self-consistently. You can quantize any classical theory, as long as you are restricting yourself to looking at macroscopic regimes, large-scale things, and you get pretty good agreement with general relativity there. It's when you start looking at very small scales, like what the quantum version of gravity tells you on very small scales or very high energies, that a lot of infinities start popping up in the theory that you can't get rid of, which is why we don't have a fully self-consistent quantized version of gravity yet. But from the philosophical perspective of quantum field theory, you should be able to quantize anything, and figuring out how to do that is just still an unsolved problem in physics. Related to this question, people asked the converse of it. Is it possible then to geometrize or treat other forces like electromagnetism in geometric terms? Well, that's actually been worked out in some contexts. You can look up something called Kaluza-Klein theory, which is a way of trying to get a geometric version of electromagnetism plus general relativity. But in general, these are two sort of parallel paradigms. One is trying to geometrize a lot of stuff, which was a big thing in the sort of early 20th century, and the other is to try to take classical field theory versions of something and then add to them the machinery of quantum mechanics to sort of get a quantized version of the world. And these two things proceed on sort of parallel tracks. It's hard to answer these things well in 30 seconds without just throwing out a lot of buzzwords and giving you what's not really an explanation, but I don't think there's really any alternative that wouldn't mislead you. You're asking very heavy stuff. A lot of you wanted clarification on how curvature of time is what's responsible for, say, circular orbits around the Earth being geodesics. First, remember that I was speaking very, very loosely. There's really only space-time curvature. You can't really break it up into separate space and time curvatures. That doesn't mean anything. But here's what I did mean. Suppose that you take a frame attached to Earth's center with clocks. That frame's not going to be inertial. And then you work out what the equations of general relativity say the geodesics should be around the Earth, and you down project them into that frame. So you down project everything into 3D spatial and temporal terms with respect to that not inertial frame. It turns out that the pieces of the geodesic equation, the things that tell you what the geodesics should be, that basically give you Newton's laws of motion as if there were a gravitational force, are just the pieces of the geodesic equation that involve time components when projected into that frame. That's really all I meant. There's actually some good lecture notes by Sean Carroll that I've linked in the description that give you a slightly more mathematical treatment of this. Go up to equation 4.22 in the link that you see below. A lot of you were expressing confusion about how 2 points on Earth's surface can both be really accelerating if Earth's surface itself is not expanding. Be careful. We're using the word acceleration here in two different and mutually exclusive senses. In the Newtonian sense, acceleration would mean put a frame of reference at Earth's center, use a clock as if it runs, pretending that it runs the same rate everywhere, and ask relative to that clock, are the coordinate positions of 2 points on Earth's surface changing? And the answer is, of course they're not. So in that sense, those 2 points are not accelerating. But Einstein says, hold on, in the four-dimensional curved space-time sense, you need to give something some kind of inherent absolute 4D geometric meaning. And acceleration in that context means is your tangent vector being parallel transported along your world line. For points on Earth's surface, that's not true. They're not geodesics. So the way that we have to reconcile things is there a problem with saying that falling frames, like attached to an apple falling at both those places, are the ones that we should really use as the standard, even in the three-dimensional sense, of non-acceleration? Einstein says you don't really have a choice. You have to do that because it's only the falling frames that are purely non-accelerating in the four-dimensional sense. The only reason why that seems to conflict with the idea of using a single frame at Earth's center and saying that those 2 points are not accelerating is that that frame at Earth's center that you're using to gauge that is not inertial. And so that shouldn't be the standard for saying that things are non-accelerating. In other words, Einstein says the standard of non-acceleration can only be defined locally in small space-time patches. If you try to talk about it in any other context, you're assuming something geometric about the world, namely that it is a 3D Euclidean world that works the way you think you learn it works in 10th grade. That simply isn't true. Finally, I do want to reference one individual comment. I Won't Tell My Name was asking what courses he would need to take to learn about general relativity. He got some answers from Winged Soda, and then he replied, okay, great, and I guess I got lots of time because I'm only going into 8th grade. That's right, you got lots of time, I Won't Tell My Name, and you're asking all the right questions. Keep learning and listening to as much as you can, even if it doesn't make sense at first. This stuff takes years to grasp, and you're getting a head start. Glad you're watching the show.